Welcome to solverfy.
For this question, we are looking at the energy that's released when we fuse two carbon nuclei into a single magnesium nuclei. Now this is the fusion reaction equation, and we want to find what is the energy released, which is the Q value. So we just take the change in the mass of the nuclides multiplied by c squared. And in this case, we'll be taking 2 times of the mass of the carbon 12 minus away the mass of our magnesium nuclide. So this carbon 12, this magnesium. Multiply this by c squared. C squared we can use 931.5 MeV per U since we are dealing with atomic mass units. The mass of the magnesium nuclide is 3.985 and the mass of the carbon nuclide is 12. From this, we should get a value of 13.93 MeV. So this is the energy that's released. Now, the next question actually involves how the nuclei actually fuse, right? So the amount of energy that is required to bring these two nuclides together is actually dependent on the potential energy when the nuclides are at this particular distance, right? So at this particular distance, right, their centers are given to be 6 Fermis apart. So what you got to do is to find the potential difference, and this potential, sorry, not potential difference, but potential energy. So this potential energy must be equals to the total kinetic energy of the system when they are very far apart. Right? So this equals to 2 times of the individual kinetic energies of the nuclei. Right? We want to find what is the individual kinetic energy. So the potential energy is given as 1 over 4 pi epsilon naught times Q1 over Q1 Q2 over R squared, where R is the distance, Q1 and Q2 are the various charges of the two particles. So in our case, Q1 and Q2, they are both 6 times 1.6 times 10 power minus 19 coulombs. Right, since they are carbon atoms with 6 protons, so their charges is 6 times of the elementary charge. The distance over here, R would be equals to 6 Fermis, so that is 6 times 10 to the power of minus 15 meters, and then we will square this thing, right, and we get, so the epsilon naught is a constant, right, permittivity of free space. So putting all the values into the calculator, you should get a value of 1.3824 times 10 to the power minus 12 joules. And so the individual kinetic energy of the two nuclei, we just divide this by 2, we should get 6.912 times 10 to the power of minus 13 joules. And this is, in fact, can convert into MeV if you like by dividing by 1.6 times 10 to the power minus 13. Right, so you can leave it in terms of joules. Now the next part, we want to find what is the temperature, right, related to this energy. We're going to use the equipartition theorem. That is the kinetic energy of the particles. This is related to the temperature by 3 over 2 Kb T, where Kb is the Boltzmann's constant. So T is equals to 2/3 of kinetic energy divided by Kb. Kinetic energy we have already calculated previously, 6.912. Kb is the Boltzmann's constant. Substituting the values in, we should get a value of 3.3 times 10 to the power of 10 kelvins. So this is the temperature that's related to the energy of our carbon nuclei. And so this tells us that this is the temperature required for the fusion reaction to actually proceed.